Hello, so in this video we're going to talk about the concept of martingale. Now I have spoken very briefly, I think a couple of videos ago, about a martingale and about what it actually is, and it's actually a really fundamental, really useful thing in financial derivatives, and it crops up all the time, kind of show that this is a martingale, okay? Because what a martingale effectively does, I mean I spoke about it before, so I've got no problem saying what it is today. Basically what we're saying is that it's a zero drift. It's what's known as a zero drift. Zero drift stochastic process. Okay, stochastic process. Now, a stochastic process is essentially, a statistical process. It's not strictly statistics, because statistics kind of deals with data and stuff. Stochastics is all the kind of stuff that kind of lies behind the statistics, lies behind the data, kind of crunching the data. So, stochastic process, and effectively it means zero drift. So, all that just simply means is that it doesn't change. It doesn't change. Okay, so, an example of that, I mean, what defines drift? Is there something that defines drift? Well, yeah, the mean. The mean will define the drift. So in other words, the mean doesn't change. Yeah, so if you have a random variable, effectively the mean doesn't change. Okay, so or the mean is equal to 0, for example, it doesn't change. Okay, so yeah, so that's one way of defining it. Let's kind of try and jump in and sort of define it properly, though. So basically, the mean. Remember that the mean can be defined as the expectation of a random variable. Okay, so the expectation of a random variable. In actual fact, I'm going to take the absolute value of this random variable because it doesn't matter whether it's positive or negative. Okay, that's just kind of a technical condition that we're going to define now. Okay, and that's got to be less than infinity. So basically, what this means is that this martingale, if it is a martingale, it just basically means that our random variable can't go off to infinity. The expectation of a random variable can't go off to infinity, or the mean. Yeah, the mean of our random variable cannot go off to infinity. It doesn't explode to infinity. Okay, and that kind of corresponds to share prices and things like that. Basically, we can't have a share price that goes to an infinite amount of money worth. It would be nice if we could have a share price that went to an infinite amount of money worth, if we're the shareholder, of course. But of course, we can't have it going off to infinity. So it has to be contained within a finite amount of time. So that's just kind of a technical condition. But here's what the martingale is actually saying. So basically, if we have the expectation of a random variable, okay, and we're given all points in time, or the value of the random variable before that point in time. I'm looking that up, right the way up to xm. Say, given that m is less than n. Yeah, so given that we've got a time period up until xm. So basically, we've got the value of the, if I just draw it out, okay, we've got xn, okay, and we start at x0, x1, right the way through to xm, okay, and basically what we're saying is that the expectation at this value, the expectation at, or the expectation of this xn is going to be the same as just xm. Okay, it's going to be the same as this. So, for example, this is today. Okay, xm is today because this is all the data we've got. This is all the data that we've got on here on the right hand side. This part of the bracket here is all the data that we have access to. Now we have all the data up to xm. Okay, so we have all of this data up until today. But if we want to find out what's going to happen tomorrow, so if we want to try and predict or find the expectation, want to try and predict what's going to happen tomorrow, well, that's just going to be the same as today. And that is what I kind of said before with the martingale. Basically, what's going to happen tomorrow? If we want to try and predict what's going to happen tomorrow, it's just going to be the same as what's happening today. And so, say, for example, it led to a paradox. So say, for example, if we have $20 today, then what this martingale is saying is that we'll also have $20 tomorrow, and $20 the day after that, and $20 the day after that. So effectively, we'll still have $20. Now, of course, in reality, we won't. But we can use this martingale principle. This is what the maths is telling us. The maths is telling us, and then we can use that to actually make money from that. It's a little bit of a paradox. So whatever the past is like, so whatever's happened in the past, all over here, whatever's happened to the past, we know that tomorrow will be exactly the same as today. Tomorrow will be exactly the same as today, and that is what a martingale. That is effectively what a martingale is, and this makes sense using this notation. Okay, we're basically saying the expectation. So what do we expect to happen tomorrow? This is xn. Yeah, so xn is tomorrow. Okay, what do we expect is going to happen tomorrow? What do we expect is going to happen tomorrow, given that we have all of the data up until today? This is today, XM. Well, it's going to be the same as today. It's going to be whatever's happening at today, and whatever's happening today is defined as XM. Okay. So, let's consider an example. So let's consider a share whose value changes each day according to the following distribution. So let's say we have a distribution C, okay, and if the value of C, so C is just our option, okay, if our value of C is 10, we have a probability of a quarter, okay. If the value of our share or our option, whatever you want, is 8, then our probability is going to be a quarter again. Okay, but if the value of our share is -9, then the probability is going to be a half. Okay, so here we have now this is our distribution. Okay, and we want to basically show that this is a martingale. We want to show that this is a martingale. So what is the expectation of C? So in order to show the expectation of C, we want to show the expectation of C is going to be equal to 0. We want to show the mean is 0. Okay, we want to show this property here. We want to show the mean is 0. Okay. We want to show the mean is 0, so the expectation of a random variable is 0. Okay, this is a this is the random variable case. This is the discrete case, I think. I can't remember. But anyway, we want to show that the mean is 0. Well, the mean is just the expectation. Yeah, we can say that the expectation is just the mean. The expectation of a random variable is the mean. Okay, so the expectation of our distribution C, or a random variable C, is 0. Okay, so what is the expectation? Well, it's just going to be the sum of n times p. So this is our n, 10, 8 and -9, these are our n's, okay? And these are our corresponding probabilities. P equals a quarter, P equals a quarter, and P equals a half. So what we're going to do, we're going to do 10 times a quarter, so we're doing n times p, okay, plus n times p, so 8 times a quarter, plus -9 times a half, plus -9 times a half, okay. So let's have a look at this. So we've got 10 over 4 plus 8 over 4 minus 9 over 2. So I'm just going to double that to make it 18 over 4, just to make them all over 4. So therefore this is going to be 10 plus 8, so that's 18 minus 18 over 4. So therefore that's going to become 0. Okay, so we've basically shown that the expectation, or the mean, is 0. So therefore it's a martingale. Okay, because we've shown the expectation, or the mean, is 0. It's a zero drift process, right? We've basically shown that it's a reason. Let's kind of link everything together now. So actually, I'll write it new down here. So it's a zero drift process. It's a zero drift stochastic process. So if it's zero drift, it means it doesn't go up or down, right? So it doesn't go up or down. If it's zero drift, it means it doesn't go up or down. Well, not going up or down, a way of showing that is that the mean is 0. It's basically showing that the mean is 0, or another way of showing that, another equivalent way of showing that, is that today, or the value today, is going to be the same as the value tomorrow. The value today is going to be the same as the value tomorrow. So these are two ways that you can show that it's a martingale. Either the mean is 0, or today is going to be equal to tomorrow. All right. So this is two ways that we can show it. Now, if it's discrete time intervals, so in other words, we actually have values that we can measure. So, for example, every single day, for example. So let's say this is Monday, this is Tuesday, Wednesday, Thursday, and so on and so on and so on. So in other words, we can measure the value every single day. This is an example of discrete. Okay, this is an example of discrete. If it's discrete, okay, it could be every second, every hour, something like that. Okay, if it's discrete, then martingales are relatively straightforward. Martingales are relatively straightforward to measure. Okay, but if it's continuous, for example, if you're measuring continuously, so this is your time, okay, and you're measuring at every single point, and you're trying to work out the martingale, then martingales are really quite difficult. So if it's discrete, martingales are easy. If it's continuous, they're not so easy. They're much harder. Okay, and the way which we look at this, okay, the way which we look at continuous, so this is continuous, right? If it's continuous, the way that we do it is we replace all of the events, so we have all of our events by some, our events, we just replace them by something called a filtration, okay, because it's much harder to deal with a continuous time period. So basically, we use a filtration to deal with continuous time periods, to kind of, deal with martingales, okay? So if we that's basically the next thing we're going to come on to. We're going to come on to filtration. Okay, so a good way of thinking about a filtration. So effectively, we want to measure the martingale. So what we do is we replace all of these events, x0, x1, whatever, by a filtration. And if you like, you can just think of a filtration as a flow of information of the process. So effectively, a filtration is a flow of information up to some time period. So say, for example, up to this time period here, this is what we would consider all the information that happens here. We just consider it like a flow, and that's all a filtration is. And we'll look at how to deal with filtration in just a moment.